Hey, Tony. I think it likes me. Good afternoon, everybody. Welcome to it, our first meeting in London. We are happy to start this working group working on new Antonio Swartz novel routing protocol for data centers. We are looking forward to working with all of you, and welcome again. So Jeffrey and myself, we are co-chairs. Eventually we'll be looking for secretary. It has to start with J, yes. Additional points. So new updated not well. Now it has all the links to relevant standards, process documents, anti-harassment procedures. Please read it and be familiar before you start contributing to IETF. IPR disclosures, and if process no different than any working group in IETF, we'll poll you when we adopt document. We'll poll you before going into working group last call, and unless every co-author responded, documents will not progress. We are looking for volunteers for taking notes and JabberScribe. Doesn't have to start with J, by the way. Anyone? Should I point? Ross White. Oh, seriously? AC? Anyone? Greg?
You're a big machine.
We do need a note taker. Thank you. Appreciate it. So agenda for today. So we are going to start with Chair's brushing, and we would also like to discuss with you approved charter and next steps. So we'll have for presentation, motivation, additional requirements, use cases. Tony is going to go in depth on RIF details, and then we'll have first presentation of Young model and extensions for beer.
There's still a few seats up front.
So milestones as defined is to adopt protocol specification March 18, which is about now. Submit applicability statement to ISG months later. Young model is in good state. We probably would need a few more iterations, but it's there. And then next year to submit security and threat analysis and submit protocol specification to ISG, and if no additional work is required, to be on fast track and be done with it. So charter as defined today is in line with milestones defined, and it's good. We are on track with delivering on time, at least so far, and we would like to hear from you what is the future work you would be interested in. We've had quite some discussion on segment routing extensions. We kind of understand how to do them. I think we also looked into how to provide different kind of resolution of next hop in default route cases. So there's going to be document describing this. Another point is beer, and there's already drafts that we are going to present. So if there are any other topics of interest, we would like you to tell us. And if someone wants to tell us now, good time. Okay.
We still have seats up front.
The first presentation is, it's not you actually, it's Jan. Jan, right? Where's Jan?
Well, if anything, this will also be a test, just how many people actually read the draft. Uh, anyway, how many people did actually read the latest RIF draft? Okay. Well, all right, thank you. Anyway, so this is actually originally RIF was designed to be a data center protocol. This was actually an attempt to look at Rift, look at its specifications, and see if it could be adapted for other use cases. And one of the use cases that that I was thinking of possibly adapting it for was the use in access networks. So it was designed to be purely informational. The primary goal of this is to actually evolve Rift into the draft has been submitted. It's hopefully there will be other interested parties looking to adapt Rift. Again, it's designed to promote Rift for use in general access networks and not just in data center networks. Obviously, mixed-use data center user access setups. Typically, those are found in what people refer to enterprise campus networks. Certainly, there's a call for various vendors so they can start considering using Rift in their what many people call integrated fabric solutions. Possibly call for open source projects and possibly to start to get other open source routing software stacks involved in Rift activities. Obviously, enterprises in quotes. It's a marketing term. It would be best not to go into a debate what's the difference between enterprise and not enterprise, because it's impossible. Anyway, I just defined it for the purpose of this discussion for user access devices and their services. Again, there's whether you call it campus or multi-tenant access network, it doesn't matter. It doesn't take away from the data center use case. Certain data centers, multiple security zones, meaning people who legacy web environments. So anyway, why did Rift even come up? First, it's a problem that's frequently ignored by many people. So the way typically people look at campus networks is, they look at it from a perspective of core distribution access. It actually very much nicely maps to the constructs defined in the traditional, Fed tree designs, and in this case, RIP designs. Mobility and security requirements. Mostly, a lot of the requirements that exist in some of these access networks are addressed by scaling broadcast domains. They're a little tough to horizontally scale. And the one thing that actually makes it a good match is the fact that Rift was actually very nicely designed as a protocol to address the situation in which at higher tiers, i.e., the tiers closer to the super spine tier, there are a lot more control plane and forwarding operations that can be done on devices at those tiers than at lower tiers. And Rift is actually very much designed to address that. So that made it a very good match. Second of all, verticoupling, stability from prefix information makes it possible to advertise any information. Like if we do actually want to do broadcast domain scaling for some reason or another, We can operate over a numbered network. Key values and policy guided prefixes simplify management and create framework for separate connectivity domains. So obviously, we wanted to kind of like, come up with a list of other requirements that could make Rift a good match for some of these like network use cases. So first is network slicing. Again, it's in quotes because difficult to define. Okay, it's basically ability to create virtual private routed network within a Rift access network. Incoming packets are associated with a slice of the UNI interface, distinctly identified at N9, associated with the proper connectivity domain, and write UNI at egress. Kind of like your traditional definition of multi-tenant networks. The goal was to kind of like, again, it is a protocol for access networks, and the goal was not to kind of like, not to have it follow the traditional IPVPN model with overlay and underlay, but to follow more of a multi-instance model or multi-topology model. Plus, our edge core model is reversed, so bringing a transport service model would actually nullify most of the benefits of Rift. Obviously, the idea was we improve on the other discovery process. We configure the slice components, we flood. So the first kind of thing that we wanted to maybe consider looking at is that in the original Rift specification, key value TIEs, which in many ways you could say are equivalent of the LSAs or LSPs, they're actually going traditionally southbound for things like, let's say, configuration. The possibility was to consider flooding them northbound, use that to either configure instance IDs, possibly borrow from the RFC 8196, which is IS other configuration. Create network instances if there is something southbound. What's installed, depending on protocol and default origination. We'll cover that in a minute. Lower tiers can explicitly request default information, and obviously address the biggest thing is that if we're going to build a multi-instance network, see how we can address the fact that we're ultimately that we're designing this protocol to originate a default downstream. So effectively, we're creating a traditional summarization problem that breaks many virtualization technologies. All right, so obviously some of the ideas were separate adjacencies for each instance. Again, just possible ideas, separate link information exchange. Again, it doesn't have to be done that way, but those were some of the thoughts. Obviously, if we're using link monitoring protocol, like for example, BFD, then maybe a single session can potentially handle adjacency for each instance. Obviously, we can negotiate UDP ports. As that we would perform standard tie exchange. We would be carrying instance IDs. Obviously, there would be separate northbound SPF and southbound SPF calculation for each instance. No different than in a single instance Rift. Install in FIBs depending on what other discovery tells us that whether it has to be installed. We can use obviously any tunneling or encapsulation technologies, and I'm sure additional drafts will be written. Obviously, nodes can decide if they want to act as a route aggregation points, because in some cases we would not want to aggregate routes for certain situations, and some of the nodes would not populate their ribs and propagate advertisements if there is no need to do so. And policy groups prefixes are leveraged for policy controls. Like if traffic needs to be explicitly forwarded to, say, security devices, scrubbers, traffic shapers, or other things that may be deployed in a traditional access network. So some of the variations, obviously no per instance adjacency, single topology, no other discovery for each instance. There's one global other discovery. So all devices are part of the same consensus group, where some kind of consensus protocols could be used to, for example, discover the leader, and that leader, populates information about instance. All right. Anyway, so prefix ties will carry instance IDs, optional parameters, and obviously whether so it's mostly how to optimize other discovery process. I can do it. I'm fine. Anyway, the other thing that typically comes up in access networks is the need to propagate external routing information from end systems. This actually may come up if the leaves and other forms of network boundaries that exist will run other information exchange protocols with upstream and downstream systems. For example, we may have hosts still, for example, running some other stack and possibly running, let's say, BGP protocol that may exist. There could be other protocols that may be installed even on other end systems. Anyway, there may need to be a possibility to flag some of those prefix ties so that we can differentiate those external prefixes. For example, if we should not be propagating them southbound, some of those prefixes may be workload specific. Same network layer addresses are given to different workloads that move around the network. So that's where we get into interesting problem of mobility that exists in access network. And what happens with some of those mobile workloads, whether those workloads are user access devices, whether those workloads are wireless devices, whether those workloads are potentially other mobile systems. What would be a good idea is to address how those workloads move around the network, meaning that if a particular network layer address appears in one place or another address in the network, there has to be a way to quickly address that. Obviously, Rift by its mechanism is designed to easily provide summarization. So as it doesn't. Nothing actually has to be propagated in the southbound direction. But if something exists in one branch in the southbound direction and appears in another branch, the idea was to possibly consider doing some kind of purge tie that's designed to do nothing else but to go and purge it. All right, possibly carrying a special mobile flag that would allow those ties to be used. And then maybe to create other systems to possibly optimize and cache things so that to address frequently moving addresses. So that was it on the mobility. So external connectivity and superspine connectivity. So often external connectivity is deployed off leaf nodes, should be treated no differently than any other external route. So the idea was that the default could be flooded northbound if such situation exists. Some people will deploy special border nodes, or superspines will act as border nodes, and those can form their own flooding domain. So the idea was to possibly start considering the east-west flooding, but there is one caveat. This is not a request to to somehow turn superspines into a backbone or a backbone area. Like if we have distinct rift domains, that's not going to address it. It is mainly to get the external information and deal with interconnected superspines. Let's see what else. Oh, so and yeah, then the final requirement that may be even more annoying to Tony, and that's another very corner case requirements for daisy chain leaf nodes. It's access network use case. It's not a data center use case. No one builds data centers like that anymore, or ever really. So what actually happens is, and it would only be allowed for the leaf nodes, and that is the level 1 nodes. It should actually be level 0 nodes. Actually form a daisy chain. It may be in fiber constrained campus environment. It may be in special environments where a lot more devices are deployed to aggregate instead of having central concentration points. It is kind of like reverse superspine use case, except now it's southbound. It is a deviation from original Rift spec, as stated by Tony. So northbound ties can go in east-west direction and leaves. Leaves still run south SPF only. Those go east-west in both directions of the daisy chain. No need for those to get reflected back northbound to ensure that there's no disaggregation loop. And obviously, no southbound ties can ever be propagated if already learned from leaf. That creates that creates a difficult situation. But if this is designed, in a constrained half-ring setup, that should avoid the need to start preventing east-west loops, and potentially again utilize the purge southbound ties in both directions to withdraw stale routes to optimize the convergence, and and then pretty much everything else is standard, and upstream nodes run northbound SPF. And purge will force all the leaves to run southbound SPF and reroute from the break of the daisy chain. That's it. So anyway, in the conclusion, these are some of the possible things to consider if Rift could be adapted for access networks. And now Tony, do your worst.
Tony P. Juniper. So can we scroll back to the first one, because you threw the kitchen sink and then some at me, right?
Hold on. I could, but
Wait a minute.
okay. It's not me.
All right. So what was all there? Because I had kind of running comments. Okay. Okay. Next one. Yes. So the network slicing merits discussion for sure, but if we start to talk about carrying kind of 2547 style prefixes with route targets.
And that's exactly what we probably should not.
Okay,
should
fine.
not. That I was basically exactly trying to go there and to not do that.
Yeah, because we're squishing the overlay into the underlay, right? And pretty soon we're like dragging the whole overlay problems into the protocol, and for all practical purposes, we start to redo BGP, which you cannot do any better.
Which basically kills pretty much most of the benefits.
Most of the justification. Okay, so next thing. So one thing I didn't understand, why you think that the default route summarization kills the tunneling. I mean,
well,
you know the tunnel endpoints, and how it's get forwarded there doesn't matter as long as you get to the correct endpoint. And if you use default route to forward, what you care at the end, you have your tunnel up.
So I wouldn't necessarily care, but if we start for the tunnel endpoints, absolutely, and that's why perhaps tunneling should be a better approach how to address this. But if some people, but if methods would be chosen to address it, let's say by building LSPs, then that may actually that may actually have problems. If collectively it gets decided that tunneling or even some kind of translation technology like XLET is actually a way to address this, that's not a problem. But if we decide that, but I guess the bigger problem becomes is that tunneling is one thing. Building a tunnel, that's not a problem. Forwarding traffic into those tunnels, that's another thing. Since we're actually that's right, I remember. Yeah, since we're actually aggregating a default downstream only, then if we have an edge device and that edge device needs to be able to route to some kind of route that long ago got summarized, it doesn't actually know that it needs to go into that tunnel. It can certainly follow default, but when it follows a default, it needs to land on a super spine somewhere, and then actually be routed somewhere southbound. So that's actually kind of like the concern about breaking with default.
But I mean, okay, the tunnel destination endpoint will be
Because
always more specific than default. So I'm getting lost.
So
We
the
need a
tunnel.
whiteboard.
So the tunnel. All right, we can
Tony,
take it offline.
Oh, okay,
I
next one.
think going through representation and then having this discussion will make much more sense for people around us.
So
You're discussing in terms of the protocol that haven't been presented yet.
Okay, next one. Next one. So one thing that confused me, and that's probably the last comment that I make, is the mobility stuff. So there is nothing special you need to do. If the prefix moves, the guy who lost the prefix floods up a new tie, which has no prefix, and the guy who got the tie floods up a new tie that has the prefix, and everything gets recomputed automatically. So there's no need to purge anything specifically.
But what about the cases in which a mobile prefix moves to a completely different branch of the fat tree?
Normal behavior. Both of them will flood up new ties, and the trees will recompute down. So there's nothing special.
But since only the default is actually being sent down,
Which is perfect, yeah.
Okay,
That's normal mode of operations. It's actually almost optimal for mobility, right? This is also designed for people running like a container for 3 seconds. It's about as good as you can do.
Also,
right.
Can we take it offline? Because that I actually even tried to simulate. Okay.
So there
Thank
will
you.
be probably
All right.
pretty much in-depth discussion.
All right, I'm
whoever
done.
cares to join. Okay. I see we got a very intimate setting, smallest room available. At least it didn't suck out the air. Yeah. Got it? All right, so first probing question. Who read the specification of the Rift? Okay, about half the room. Who read it more than once? Still.
The next question to understand.
Well, I mean, the introduction says it all, right? What is the precondition to read the stuff? Okay, so I think people have an idea at least what kind of mechanisms are inside. Maybe even they didn't understand in detail. So this presentation is not necessarily like tearing apart how the stuff works in detail, okay? But more like where do we still need work to be done and what is kind of well understood and needs to know like precise specking out. So I'm kind of laying out the landscape. How far are we? And if you stick to the end of the presentation, I have a nice surprise. So, you know, there's something sweet at the end. All right, so objective failure of technology. All right, so this is kind of a traffic light representation where we are. Red is like, not attacked yet, completely open. The green stuff is fairly well understood. The really, deep green stuff is really well understood and already spec'd out. And the orange stuff is somewhere in between. And those are kind of the elements that represent the protocol. Some of them are optional and some of them are like basic mechanisms. So going from the left, the whole thing is like a mind map, right? A little bit just thrown out there on purpose. So the formation of adjacency, the lie rules are, that's fairly well spec'd out in a lot of detail. But, we still, I will break it down there. What are the components of each of those and how far are we and what still needs to be done? The schema versioning and sharing and possibly doing the schema in another ideal, like gRPC, is somewhere in orange. And I think there's a lot of interesting work that can come out of this working group that will carry forward. If we decide to build more schema-oriented protocols, we will face the problems that we will be facing here. Like, how do you version the schema, right? Is the schema a separate document? What happens if multiple people work at the same time on the schema? How do you reconcile? Would we rely on optional elements? We will have some kind of a capability field? Or we will like periodically release like combined version? Those are kind of unresolved things, right? Because we have this kind of mandatory optional indication. Like on TLVs, is a mandatory optional element, but how do you reconcile all these works into a schema version? So when I open a protocol and a peering, I know which schema we're talking about, what's in the schema. The route redistribution, which was a lot of this like yen stuff, is kind of not attacked yet. I have some ideas, but nothing has been written, right? So how do you redistribute into Rift, and how is Rift redistributing? How is that work in deployment scenarios? An interesting thing is the fabric bandwidth balancing, which came into 05 draft, and I have newer ideas, and I will present in details what I'm seeing as requirements. Rift seems to allow to load balance bandwidth on the fabric without any traffic engineering in a coarse way, very cheaply. So that looks like something that appeals to a lot of people who have a lot of asymmetric bandwidth on the fabric because they're losing lag constituents, they're provisioning links, whatever not. We have the transport, which right now is basically flooding over UDP. And people desire to run maybe TCP, maybe Quick, maybe run it over L2. The work is possible there. We could do this kind of stuff. But right now, there's basically one version defined. The PGP is written down, and there's some work on policies and communities and so on, but the stuff is still not very firm. The flooding scopes, the flooding reduction is actually, I think, quite well specified. It will need firming up, but the problem is understood, right? I mean, you can do much better than ISIS, frankly. The ZTP is fairly well understood. The procedures are very firm in the spec. The implementations and the leaf and open source is kind of like, this is not a traffic light. It's something that people should attack. Something is happening, but not much. Security schema elements. So I mentioned something about how can we make this protocol, the security support, easy. Because link states were struggling with security in a couple of places, and we know the pain points. But we learned the pain points after the protocols have been designed and deployed. So I say something about that in more detail. So there's some SR and beer support. That's something that is optional sideways, right? But those things haven't been attacked yet. So there's some beer work going on, and there's some talking about SR. I'm not convinced about the SR use cases in the fabric, right? So that's something that maybe should be attacked sideways. And people talk about what are the real use cases and whether we should support SR at all. The key value store, something has been written down, so that's in some orange state. The yen configuration operational state models that's being attacked, I put it red because nothing has been done until today. The southbound default route origination, I think, is fairly well written down, and we understand it, modular, all these desires of people to support east-west links in different ways. But this as east-west link stuff is delicate because the moment you start to use them bidirectionally, you start to build loops. And you lose a lot of these, loop-free properties of the protocol very, quickly. The moment you use the loop-free properties, a lot of the goodness goes out. And you start to slosh a lot of topology information, different places of the fabric. So also this minimal blast radius starts to go away. But that's an ongoing discussion, how far we get there. I think the requirements has been fairly firmly set down, and they didn't seem to evolve farther over the last couple of months. The automatic disaggregation is pretty well understood, but there is a whole piece which hasn't been written down, which I call the transitive piece. The computation is somewhere in between. So we should write a proper all paths computation, which is not too difficult. But today we basically put just an SPF into the spec because that is something that people grasp very easily. But what we really should have is all paths on the fabric, or K-best paths on the fabric. And the BFD SBFD procedures are kind of decently well written down, but that's also something which is more like in orange state. I consider deep green when we have firm procedures and FSMs, right? So an implementer can sit down without thinking much, just hack this out. So this, BFD support is not in a green state without consider. All right, so now I basically take each of these pieces and start to go a little more detail. All right, because I'm giving you this mind map, what needs to be done, where are we with the whole thing. So requirements should be possibly split into a completely different document and still being discussed out. I think they're fairly firm, but they're just not part of the protocol spec as far as I see it. I mean, I'm talking right now about the Rift thing, which was the container that had everything, carried in it. So now let's talk about the schema in a little more detail. So around this schema management, and that's kind of larger than the Rift discussion, will we go towards something like a schema-defined protocols for all the benefits we're getting? We're being faced with new problems, right? How do we progress standards along something like a schema-defined protocol encoding on the wire? So the first thing is, how do you version the stuff? And that, I think, is orangey. So we understand how to version a schema when things change on a schema. And we can actually automate it fairly well. I mean, we also do it with Yang models and so on. So I don't think there is a lot of magic there. But then we have to ask ourselves, how do we share this one schema when multiple drafts start to evolve in a working group and add elements, right? And there's multiple approaches. We could basically say the only thing you can add in a new draft is an optional element without default, which is basically an optional TLV that people don't have to understand. But that's kind of limiting, all right? Because if you do an new optional element without the default, you don't really have to bump up the schema version. We could have some kind of capabilities with mount points, just like Yang, all right? But then we would have to start to extend the existing ideals, because beside Yang, I wouldn't know that anything is doing augmenting well. We could do some kind of a periodic schema reconciliation. So say every year we're releasing a new protocol version, and once a year, new capabilities make it in, but that's kind of this artificial gating, on these checkpoints. And schema should probably be a separate document from the spec. All right. Now, support for other schema languages, because some people are talking about it. Nothing has been done, it can be easily done. I mean, you can write it in schema language of your choice. They are not that different. How much value it represent, I don't know. And a problem that's coming up is that stuff like Thrift of gRPC is not strongly standardized as we understand it, right? So they don't have ISO documents we can reference to, and are very stable. There are reference implementation, there's some documents, but those are not strongly standardized things. So how will we progress protocol spec if the schema language in itself is not really strictly frozen? Those are kind of open questions we face if we go into this direction. Then there is, of course, the idea of doing some comparison between different schema languages and what would be best to actually implement, a schema-oriented protocol and so on. This is all kind of larger than Rift, but those are the things that start to emerge when you start to go in this direction. All right, so where are we on the hello formation, on the lies and the adjacency formation? So on the FSM, we have nothing written. I did it kind of on purpose. I mean, I don't want to firm up the protocol too quickly. It should be still discussed. And when this FSM is being strictly written down, a lot of details may still emerge. So that's a call to action. Somebody can start, I provide the first FSM, and they start to gather the procedure and write the FSM and start to firm the stuff up. The zero-touch provisioning negotiation is kind of fairly precisely written down, and it should sink into those procedures of the FSMs, in the actions on the FSM transitions. We have security hooks, so that's orange, right? We don't have the security spec'd out fully, and I show some ideas that I see emerging, working on it. And we didn't say anything about DFO addresses, DFO UDP ports, the DFO multicast addresses on which Rift runs. So there's no assignments. That's more like a detail. All right, so transport. Again, a bunch of things. So the UDP transport is pretty well defined. Okay, that's not a hard thing. So we basically flood over UDP. And of course, that merits a discussion. So we don't have an L2 snap. We don't have an L3 IP protocol. I do not consider a desirable direction from, having learned what that all means in terms of implementation. So I consider the UDP for data center use, which is what I'm aiming at, good enough. And it has a lot of very elegant properties like, multi-instantiation is almost trivial. But maybe we should be doing other things. And in a sense, Rift has been laid out that is agnostic. So when you build the adjacency, you could negotiate, what you flood over. Well, flood over TCP if your neighbor supports that. Is there a lot of value in it? I don't know. But those are like the things on the table. So we don't have the TCP support, and right now we don't have this transport security. We just have the hooks. And how far should we take the transport security? We have all those discussions from the security area coming out, like, do we need confidentiality on routing protocols? And I don't have the answer, but I'm just saying that's like an orange area, right? The hooks are in, some stuff is here. How far should we take it? Should know who's willing to work on it, basically. All right, so ties and flooding. So here it gets interesting. So the flooding per se, the scopes and the procedures are pretty well understood. It's all stolen from ISIs. I mean, the scopes are novel, but otherwise flooding, ISI is pretty much nailed. What can be done. We don't have, of course, the final state machines, and the procedure. So that's something that could be poured in concrete nicely, right, to make it like a grown-up spec. And when we start to serialize and deserialize, and especially start to talk about security, we start to observe that we can do things that we did with flooding on the traditional protocols better. So what we really want is to take somebody's flooded packet and use the binary form without even deserializing and serializing. And what forces us to deserialize and serialize are basically, in case of tie, the lifetime, right? That's where we always struggle. So we have this funky checksum that don't protect it, and then we have this binary form. We always flip the lifetime and then push it forward. Now, if you deser, you cannot take a serialized version of a model and say, oh, I know where the offset is of this field, let's flip it on. So you have to deserialize, change the lifetime, and serialize. This is tricky in a couple of ways, because you serialize and may produce another form which is perfectly valid. So I'll give you an example. If you have an optional element with the default, I may receive this element being omitted in the encoding. When I deser it, my deserializer may choose to insert the element with the default value. So when I serialize it, I get a different binary, right? So ideally, I want to just propagate the binary version, so I have to take the lifetime out. So I'm thinking that, there's some laser thingy here, that stuff, that we basically need to frame a serialized object to do routing well into its own envelope, which holds multiple things. So let's say we do it over UDP header, but it really doesn't matter. Some kind of transport. And we want to take the security fingerprint out of the packet, right? So here's a security fingerprint. So we basically say, I may have a security fingerprint, I have some length, which indicates I have a security fingerprint, which comes later, which is a SHA, which protects this whole thing. The object plus something I'll talk about. And the tie lifetime, we never SHA them. right? Today they're like this funky thing, like set them to 0 and then compute the checksum and do a lot of, you know, funky stuff. We actually shouldn't even have it in the serialized object, in the tie. That stuff should be carried on an envelope. So when I get something like this, I can very easily just update the tie lifetime and just push it out the box again. I don't have to touch the SHA or anything or any of the serialized object. I don't even have to deserialize the object if I choose. Right? Because think that if I have to deserialize, change the lifetime, serialize, and then flood it on, I'm incurring a delay. What I want is to really push this thing by just changing the lifetime. The other thing that we should be taking out the envelope is the line nonces. So what does it mean? When I'm producing a SHA on my hello packets, on my lies, it's trivial to mount a replay attack, right? So what I'm doing is I have to show my nonce, which is randomly chosen, and my neighbor nonce that I'm basically reflecting, and I'm doing a SHA every time over the whole thing. So I think this is a work that needs to be done if we want to do the maximum speed flooding and good security support. Okay, and I'm not even talking whether this is encrypted. I mean, we could also encrypt that stuff as long as we don't touch the binary. Okay, so local flooding reduction, I think that has been written down. That is in kind of an orange state. We understand it. Actually, it buys us quite a lot on the fabric. The global flooding reduction is a long discussion. I had with Pascal yesterday, like 4 hours. I think we understand how to do on the whole fabric global flooding reduction very well. Okay, but that's a very interesting topic because we can literally squeeze flooding to a trickle. Okay. All right. So PGP. I think we don't have the schema definition yet. We have some of the policy definitions. So the PGP is kind of work in progress. Some stuff has been written down. How hard this thing will be driven will also depend, of course, on the deployment scenarios, use cases, and customer demand. ZTP. So zero-touch provisioning. So we are lacking the final state machine, proper write-down of that stuff. But I think in terms of understanding the rules and elements that we put on the lies and the level selection procedures, that stuff is all very firm, well understood, is actually running. Automatic system ID selection, I think, is solved fairly well, would benefit from another look over it. Automatic interface addresses, it's something that right now, for all practical purposes, looks like, link local v6 is about what you want to do on a fabric. But that's something that may merit further discussion. Rift doesn't need any addressing whatsoever except to somehow get transport over something, which possibly preconditions addresses unless it's some kind of point-to-point. The reachability computations, so what we're missing is the proper write-down of the all path computation. Because, if Rift is loop-free, I can actually use all possible paths. I don't have to constrain myself to SPF, the way the spec is written today, just to make it simpler to understand. And the east-west links is an ongoing discussion. I think the way the spec is written right now, using the east-west links for protection has a lot of benefits. It remains loop-free and gives you a protection, and it does not play havoc with your blocking probabilities. Automatic disaggregation. So the normal scenario, why do I have it? I would say it is more in the greenish. We understand that fairly well. But there is, on very poorly connected fabrics, basically butterfly designs, there is a case where we'll need the transitive disaggregation. And I will not go far into the depth here because that will take about forever. Stuff is written down, understood, but it's not in the spec. Southbound default route origination. So those are kind of like the pieces of the protocol, how the protocol is put together, right, to make it work. The default route origination southbound, I think, is pretty well, the rules are fairly firm. The interesting discussion also in application to the things that Jan was talking about, it may become interesting if we start to redistribute something like, okay, here's my internet reachability, here's my default route. So then you don't want on the fabric to originate default route because you have two default route, unless we start to basically have an external default route. And we can do that, okay? But that also merits thinking whether we should have like a fabric address range, which is the internal range, right? And use this prefix instead of the default. So what happened on the bandwidth balancing? So that's some interesting work. So next draft update will have that in. So the current draft has a version of bandwidth load balancing, which after the first experiment implementation has been vastly improved upon. So how can we cheaply load balance fabric? And I'm just showing the northbound direction first. So if we are somewhere at a leaf level, and we have a tons of like 10 meg links, and we have a bunch of 100 meg links at the next level, we have imbalances, right? So let's say this link is not here. So we only have 10 up here, but we have 20 to this guy, and he has 200 up. This guy is only 100 up, but this guy has symmetric bandwidth. So how do we weight the default route to give a coarse load balancing? Right. So the way we can go about the stuff is that having all the information, which we have enough information flooded down, and we do it from this level to this level, and the next level does the same kind of load balancing. We talk about something which is a bandwidth adjusted metric. So we have the normal metric of the route being distributed, but we also have all this bandwidth information. So we compute from a leaf a sum. First we have the bandwidth from a leaf to the next node. So here it will be 20, and here will be also 20, but here it will be 10. And then we also have the total node bound capacity on the node that we're reaching. So this guy will have the total capacity 200, and this guy would have 100. So when we receive a default route, for each of those default routes, we basically look at the sum of the both. So when the leaf 112 gets a default route from 111, it knows that it gets 20 and another 100. So the sum is 120. So that's the sum. So total, of the leaf to the north and north up. We take this bandwidth number and we push it to the next power of 2 and take a log 2, which basically means we take the most significant bit of what we got in terms of bandwidth available, right? So as an example, leaf 111 to node 111 goes this way, 20 plus another 200. So what? I miscalculated? No, I didn't miscalculate. So it's 220. So when you go push it up to the next power of 2, it's 256, which is the 8-bit. Okay? And now from all these available default routes that go up, we built this, what is the highest bit? We take the highest possible and we basically subtract. So how does it work? If the highest bit is 8, then I'm taking the maximum, which is 8 minus 8 is 0. I do plus 1, and I use the normal distance, which here is 1, as a multiplier. So we will end up with 1. So when I have 220 bandwidth, I end up with the 8, which is the highest bit, and 8 minus 8 plus 1 is 1. But if I go to node 111, okay, here I only have 10 plus 100. So I have 110 total, which is 128, which is 7-bit. So when I do 8 minus 7, the maximum, I get 1 plus 1, I get 2. So that way I end up with the weight of 1 to the node that has more bandwidth, and the weight to 2 that has significantly less bandwidth. Basically, each time I see half the bandwidth, I basically give it an off. It works out very nicely, basically load balancing with or weighting your ECM, your default route, depending on how much bandwidth you see going up. And that all works independent of the administrative distance because Rift is loop free, right? So I can literally send it either way. It will make it. I do not have to follow any kind of shortest path. So where are we with the stuff? So the northbound balancing, I think, is decently well understood, worked on. The southbound balancing, we didn't do any work yet. Question is it even necessary? I don't know, because it leads to all kind of like ugly fishtail problems. It's much harder to define what you want to do when you're going down into the fabric. What is really the available bandwidth that you have? Of course, this depends on what is your ratio of your east-west to north-south traffic, right? If all the traffic goes north, this works very fine. But what if the traffic turns around here to a large degree? then this bandwidth really upstairs doesn't matter. So it's very similar to like the oversubscription ratio on the fabric. So should we allow for a constant people can configure? You know, I have no opinion. I think this is a very good first approximation of a coarse load balancing. And then if you need the fine-grained balancing, then you have to understand the characteristic of your flow. So you have to shape on the edges, or you have to do per flow traffic engineering, or you have to do some kind of, you know, utilization measurement here and do it real time on a fast path. I don't think that's something that lends itself to be implemented in the control plane efficiently. All right, so one more, the key value store. I think the schema is there. The use cases none of this is written down. People have a couple of very interesting use cases for the key value store, but that has not been formalized. We don't understand the maximum scale of what will be this key value store capable of. And I think we have fairly decent tie-breaking rules, you know, when multiple people start to advertise the same key value combination. So other technology and loose ends. So the segment routing. So there is some section suggesting how could we support segment routing, but what are the use cases really, right, for the segment routing? The most realistic use case is kind of pinging through the fabric a fixed path to understand, is the path, you know, operational? There's a bunch of other possibilities. There are ICMP extensions, a long time, you know, defined ago. You could target interfaces and so on. So I think it's a slightly contrived use case. Beside that, segment routing, except like egress peer engineering, I didn't see any fabric use cases I was convinced of. And egress peer engineering could be done using, you know, like exit points prefixes, in my opinion. So the beer, something will be presented. The BFD, should we support something like SPFD? I don't know how familiar people are with that. That preconditions that we basically have like unique identifier on the whole fabric. Now, how do we get those unique identifiers? I was thinking through that stuff, not clear. So the Yang models will be presented and the route redistribution. Those are like the kind of still widely open fields that are just being started to being looked at and worked on. Cool. So the sugar at the end is that we will be putting out publicly available binary that can be downloadable. Actually, stuff is ready, but you know, getting the stuff through all the red tape and put it on a web page so people can actually click it and obtain it. I'm in the last steps. So it's a standalone binary package, runs on OS X and Linux. I'll put announcement to the list when I have the download link, you know, God's willing. Large parts of Reft are implemented in this thing. It has an environment where people can very easily build fabrics. So you can build fabric of your liking very easily using some Yang schema and just push it up the hill and run it. And you'll run a Reft per switch and get all kind of statistic and stuff out of it. You can actually use it to interoperate your own things again, because it runs on UDP. So you just specify a UDP port that sticks out through the Yang, and you hook up your own thing on this UDP, and you're in the game. Okay. And of course, open source implementation encouraged. And the important thing to say here is that the Leaf version is much simpler to build, right? So it's about 20% of the effort to build Reef is to build the Leaf version. And why the Leaf version is interesting, because we could start to push the Leaf versions towards the server and stretch the control plane in the fabric all the way to the hypervisor. Okay. So that's all I have. Questions? Everybody died of heat stroke. I think temperature like 99 here in this room. Thanks. Suffocated? Dazzled with brilliance? No? Okay. Good. No question. I did perfect. Thank you, Tanya.
Good afternoon, everyone. I'm Zhenzhang from ZTE. You can call me Sandy. The first presentation is for Rift Yang. In this draft, we have co-author Wen and Xufeng. This setup model is defined according to the Rift protocol draft written by Tony. This model includes protocol configuration, state information, and some notifications, and the to-be-defined RPC. Some features are added to enhance the protocol. Let's see the Rift configuration. But we know that because Rift is very flexible, so we still like some feature in this model, so we will add it in later version. In existing Yang model, we can see the configuration includes node info, interface information, and policy information. The base node information includes node system ID, address, node level, and the other information. And the policies include the community and the policy guide information. And the features can be defined to enhance the protocol, such as BFD, flooding, reducing, and the overload bit and the default route origination. Let's see the Rift state. Until now, we defined 3 kinds of state in this model: neighbor, database, and key value store. This is the neighbor state information. We can see the neighbor system ID, address, the level flag and value, and the other information. This is the database state and the key value store information state. So from it, we can know that the detail of the type and such as the originator, the direction, the link type, and the sequence number of the lifetime and the other information. It's the notification of the Rift. Until now, we defined 2 kinds of notifications for it. One is the unexpected type, and the other one is the neighbor's layer error. So we can improve it in later version, but we think it will help people to understand Rift protocol well. Maybe some different benefit for someone. Okay. This is the Yang. Any comments? Spelling mistake. You should point it out and we can improve it. Thank you.
Thank you.
Okay, before the next slide, can I ask where the blue sheets are? If you have not signed, please sign the blue sheets.
And the second presentation is for Beer with Rift. We have co-author Jeffrey and Wen. I don't know how many people understand the Rift protocol well, so I make a brief introduction of Rift protocol here. Rift is a hybrid routing protocol for closed and fat tree networks. And for northbound, we use link state routing. And for southbound, we use distance vector routing. And in southbound, the default route is used most of the time. And some specific disaggregation routes is used to avoid black holing or to provide some optimal routing in certain situations. So there are 2 different features in Rift protocol. You can remember northbound and southbound. So because there is 2 different features in Rift, so we use 2 different signaling for beer information advertisement. In northbound, we use the existing defined of beer SPF or beer ECEs like mechanism to advertise the beer information. And for sourcebound, we use the function defining beer prefix redistribute draft to flood the beer, such as BFID and the other information. Because MPLS is not always used in data center, so we also provide the non-MPLS encapsulation. So the only real difference between non-MPLS and MPLS encapsulation is the BFTID. So we just distinguish the key value. We can get the right encapsulation. So about the signaling, because in MPLS, we just use a label block in MPLS encapsulation sub-TLV to advertise the beer information. So we can reference the function. In non-MPLS, we can simply use the unique combination of subdomain, bit string length, and set identifier. And also we can use the function just like MPLS case. We use the BIFT block instead of label block. So we can advertise the beer information very well in Rift protocol. So it's a summary. So for northbound, we can see that we use beer, OSPF or ECs like function to signal the beer information. And for sourcebound, we use the mechanism defined in beer prefix redistribute to advertise the beer information. So similar BIFT ID signaling for both MPLS and non-MPLS encapsulation. And also we can use Swift schema to instead of sub-TLV format. That's all. Any comments? Thank you.
I have a quick comment on this one. Yeah, so it's this work is not in the currently in the charter for Rift or in beer. This is just to show that when the Rift progress, the beer can also nicely work with Rift. This is something that's thought process going on.
Yeah.
And in general, practically looking, while we try to kind of decompose the complexity in this meeting, next meeting, I think we'll try to go into perhaps higher level, but more applicability, how different features of Rift can be used, how schemas are different than TLV-based encoding, how we can easily extend, experiment, innovate based on Rift and its unique properties. So the target for first meeting was really to bring knowledge of what Rift is. Going forward, we'll try to expand and make it, if not more appealing, show you how appealing could be when you understand the use and use cases of it. Thank you, everyone, and Roger.
Right now, so we were talking about pushing for the
So